Okay, good afternoon and welcome. We're going to go ahead and get started with some problems that we're going to solve today. So, welcome.
Special announcement. Flippin' Physics. After 7 years.
Yay! Okay, no reactions. That's fine. It's cool. So, okay, we're going to calculate translational acceleration in terms of forces. So, do we have any ideas of where to start? And y'all can, if you want to answer verbally, you can turn on your mic and then turn it off once you've responded. Or what we've been doing is typing in the Go live stream. Jayla, we're on slide 46. Yeah, this is a really tough one to start with. So let me ask you guys a question. How do I want to start this off? What is causing the angular acceleration of the pulley? Okay, the mass. I disagree. I don't think it's the mass, simply put. Because that's actually not specific enough. Let me kind of put some animations on the slide. Closer, Gabe. The force of gravity on the mass. Okay. Almost. So what is causing the angular acceleration of the pulley? The pulley meaning the circle, the wheel that's up here. What is causing it to spin? Okay, the weight being pulled by gravity. So then you're saying the force of gravity is what's causing the wheel to spin? But that's not actually what's causing the wheel to spin, though. There you go, Jayla. The force of tension in the wire that's causing the wheel to spin. So as this mass drops, okay, it's connected by a wire, right? So the force of tension on the mass that's falling is what's going to cause this wheel to spin. So kind of stepping backwards a little bit more, we have to set up an equation for angular acceleration in terms of forces. So I'm just going to write alpha, right? Oops, that doesn't look good. Okay, so we're looking at angular acceleration first. So there's a really important formula that can describe angular acceleration with a force. So we're looking for an equation that could connect the force of tension with the angular acceleration. And what we have to kind of go back and think about is how can we define the force of tension? So the forces of tension is what's causing the wheel to spin. There you go, Gabe. So the force of tension, typing it out, force of tension is causing the wheel to spin. Yes, Gabriel, the force of tension is acting as a torque. So you already said it, Newton's second law of rotational motion. So I'm going to write that here. The sum of the torques is equal to the moment of inertia, or I, times angular acceleration. And this is where we want to start. Okay, so we want to start that there is some angular acceleration, and that angular acceleration is being produced by a torque. Okay, so how can we derive this further? Let's derive on the left-hand side first. Okay, so how can we derive the sum of the torques? Yes. Okay. Thank you, Gabriel. I was just going to ask you that question. So, the derivation that you're going to do is you got to look back in your notebook that a torque, and remember there's only one torque, that's force times R times sine theta. And Gabriel, I want you to be really careful with calling that T. You know, be really deliberate as saying the force of tension times radius times sine theta. Okay? So normally I'm just going to back up a little bit because I really want y'all to get this and ask a question if you don't understand. Torque is derived by, or is known as, a force on a radius with the angle between the force and the radius. Okay? And Gabriel kind of jumped it already, and he said, well, the force that is providing the angular acceleration is Ft, the force of tension. So that's why we're going to put here not just force, but force of tension. Okay? Because I mean, I don't know if this is possible. I'm just saying, like, what if it's a force of friction that provides a torque? I don't know if it's possible, but then we could derive force of friction and make a bigger equation. Okay, so let's go ahead and go to this side. And how do we want to? I don't think there's actually anything that we can derive on the right-hand side because we're already given I. So we're going to go ahead and just say I and then angular acceleration. So we're solving this question in terms of forces, right? So the next step that we're going to do is we're actually going to solve for the force of tension. So go ahead and do some algebra, and how would we solve for the force of tension? What equation would we get where Ft is by itself on one time or on one side? Okay, FTI alpha over R sine theta. Okay, so good job, Mia and Gabriel, for giving us that algebra. So what we've been doing is we've just been looking at the pulley so far. So we've only been looking at the angular acceleration of the pulley because the pulley doesn't have any translational acceleration or linear acceleration. So what we're going to do is we know that there's a conversion factor between alpha, right, and acceleration, and we're going to have to use that eventually. We're just not going to use it right now. So what I want to do here is I want to find what's the relationship between the force of tension and angular acceleration. So what number can I put in front of angular acceleration? So to figure that out, you're going to plug in some numbers. So you're going to plug in the number for I, R, and sine theta, and you're going to give me a number that should go in front of alpha. So if theta is not, thank you, Gabriel, if theta is not given, then we're just going to assume that theta is 90. Good question, Mia. I did not get the answer to be 8. So check your calculator, make sure you're right in the right mode. Yeah, that's what I got. I got 4. So it should have been I, which is 2, and then the bottom is 0.5 times 1. So 2 divided by 0.5 is 4. Everyone okay there? I was 2, right? Divided by R was 0.5 times sine of theta is 1. So 0.5 times 1 is 0.5. 2 divided by 0.5 is 4. Okay, so to save room, I'm going to put that we solved for the force of tension from the pulley, and we're going to erase all this work, that the force of tension equals 4 angular acceleration. So to remind you, why did we do that? We want to solve for linear acceleration, and the only way that we can solve for linear acceleration of the block is to get the idea of what the force of tension is, because that's the connection in the system. There's a connection between the pulley and the block, and that connection is the force of tension. So the only way we're going to go from the wheel to the block is to look at the wheel the pulley first and then go down to look at the forces that are existing on the block so that we can get this A over here. Okay, so I'm just erasing all that old work, and of course I erased something that I wanted to keep. Oops. The struggle is real. Okay, so now we're going to move to the block. So how are we going to look at the linear acceleration of A? What's a relationship that we can set up to solve for A? Yeah, Gabriel, we can use that one later, but we don't have a number for angular acceleration, so we can't solve for A that way. Ooh, good job, Mia. A equals sum of the forces divided by M, which can somebody tell me what it's gonna give it away, what law that is or idea? No, not Newton's first law, Newton's second law. So sum of the forces equals mass times acceleration. Okay, so I can look at the forces. I have the mass, right? Did y'all see that? That was a clue. I have the mass. Now I can find the acceleration. Okay, so drive. What are the sum of the forces? So what are the sum of the forces acting on the block? Or simply somebody can tell me what forces are acting on the block and then we can figure it out later. Yes, thank you, Jayla. Tension and gravity. So now we have to kind of figure out how we're going to take care of the direction. So what we did when we were studying dynamics is that if something was moving downward, then to take care of that awkward negative, then we just considered downward to be positive and upward to be negative. So if we can do that here, I think that'll make things a lot cleaner for us. So what do we want to put for some of the forces? If we're going to do that, downward is positive and upwards is negative. Yeah, Gabriel, it would be Fg minus F of t. Because Jayla, in this case, the force of gravity is pointing downwards, and we want the downwards direction to be positive this time. So that's why we're going to say the force of gravity is a positive number, and the force of tension is a negative number. Or you can think about it this way, that the force of tension is going to restrict the acceleration. So remember, we want A. So what can we start substituting here? Good. mg. Okay, bye, Justin. I think that's Justin. So I wouldn't substitute for angular for FT quite yet because we don't have a number for angular acceleration. So let's just keep FT as FT right now, and we'll show you why later. Did everyone bring masks to the party? I don't know. FT is a party pooper. Sure is. Okay, what we actually want to solve for here is we want to solve for the force of tension. And can anybody tell me why we want to do that? Why solve for FT again? No, Gabriel, that's not really the right answer. Why would um, we could use it to solve for angular acceleration, but what's the significance of solving for the force of tension here? So we solved for the force of tension. Yes, Jayla, very good. So the force of tension is what's connecting the system. It's connecting the pulley to the mass. So the force of tension is directly influencing the linear or translational acceleration of the block. So it's important to know the force of tension because that's connecting the block and the wheel. So solving for force of tension, and guys, I'm telling you, this is a hard problem. This isn't like something easy that we can, that we could do by ourselves. This is one of those more challenging problems. So what would the force of tension be equal to? And remember, we're about to solve this problem in another way. So if you don't like doing it this way in forces, then you'll get to see if you would like to do it in terms of energy instead. Yeah, that's correct, Gabriel. I'm just gonna kind of make it easier for us. I'm gonna say mg minus ma. So I just distributed the negative through. Okay, before we go any further, because I need to point this out for you. What is true about this force of tension and this force of tension? So there's a force of tension that's acting on the pulley, and there's a force of tension that's acting on the block. What has to be true about those forces or those two tension forces? Yes. Good job, Gabriel. Yep. They're equal magnitude. You got it, Jayla. So that's what I'm setting up here is that the force of tension in the pulley So 4 alpha is going to be equal to the force of tension that's on the block. Yeah, Mia, good. They're equal but opposite as well. Okay, so I want to solve for Ft, right, in the block. So that's our end goal that we got to, is we calculated the force of tension in the pulley, force of tension in the block, knowing that these two force of tensions should be equal to each other. And from that big concept of the force of tension is the connector in the system, that's how I can get all the way to A, okay? And we're doing this derivation or problem because solving for linear acceleration is going to be the hardest part. So imagine if I just had you calculate angular acceleration. That might have been a little easier if I gave you linear acceleration. So by doing this problem, we're going to be able to solve for other values here too. So let's plug in some numbers over here so that we can get an expression that will leave A for us, but give us some numbers here. So leave A alone. You're not solving for A. Good, Gabriel. So I'm just going to make 4 times 10 to be 40. And then what's the unit on that? Newtons. Minus, and then the mass here is 4A. Okay, so now I'm going to come over here, and this is where things get interesting. I'm going to put the expression we just did, 40 minus 4A. Okay, so here I have A. I'm almost ready to solve for it. And I mentioned this earlier, and I think Gabriel got to it too. If we're looking at angular acceleration, we can also look at linear acceleration from angular acceleration. So what did Gabriel say earlier? What was the equation that we could use for angular acceleration? Or linear acceleration, however you want to put it. So the question is, how am I going to get linear acceleration from angular acceleration? What's that relationship? Jayla, which one's alpha? You're going to have to type out alpha. So she says alpha equals R times A. Okay, thank you. It's like I can hear your voice saying, no, wait. Oh, okay, hold on. Okay. I keep messing this up. I'm new. So, wow, I'm really new because I keep doing the same thing over and over again. Move the size. Okay, so A, linear acceleration equals R alpha. So then if I want to replace this alpha and I want A, right? So then I'm going to substitute alpha here for A over R. Ooh, that looks terrible. Hold on. Ugh, it's like a nightmare. Oh. I hope y'all are laughing at me. So thank you. So A over R. That's supposed to be an A. Now, if y'all do some fancy algebra, you should be able to solve for A. Because R is a given. I guess to kind of make the algebra easier, what we should have done is taken care of this 4 right here and just went over to the other side and divided by 4. So then it would be a little better math. Here. I hope you guys know what I'm talking about. 4, bringing it over 40 minus 4 divided by 4. So I can change this side to be 10 minus A. Units, Jayla. Girl, what did we just solve for? We solved for linear acceleration. Ugh. Thank you, Gabriel. Coming in strong. So I think, okay, yeah, math is leaving my brain too, Mia. So does this become 2A on this side? And then its radius was 0.5 times 10. So then that's A equals 5 over 2. I hope that's 3.3. Mr. Woodsaki, 5 divided by 2, is that 3.3? Oh. No, I guess 5 divided by 2. Oh, that's 2.5, huh? So what did I do? Yeah, I got you. I guess math is leaving both our brains. Jayla, Gabriel, hello, help, help. Can y'all send like a picture of what you're doing? I don't like the algebra. I feel like this is such simple algebra. We should know how to do it. I feel bad for myself. Okay, so I'm just going to erase this nonsense because this is wrong. Okay, so A, I could just have this right. Oh my goodness. I can't wait till my expensive pen comes in the Amazon. A equals R parentheses. Oh, so you gotta distribute the R, huh? That's the good algebra. Okay, so then it's A equals ten R minus AR. Okay, so then A minus or plus AR equals 10R. I think I'm okay. I don't know. So 10R is just 10 times 0.5. So that's 5, right? So I'm just going to change this to 5. Lord. And then what? You distributed the A? Oh, factor. Yeah, that's the right word. 1 plus R dip. Yeah, I don't like algebra sometimes. So then 1 plus R is, yeah, 1.5. Because R is a given. So 1.5A equals 5. So then 5 divided by 1.5. Yeah. Ooh, y'all are so good. Oh, yeah. Hold on. Let me put the right thing. Okay, good job with that algebra. I hope that was refreshing. Yeah, that was a big brain. Okay, so some of the takeaways here, we had to go all the way back to dynamics and remember for a system like this that the force of tension is equal to each other between the two parts. And what we did is kind of those old Atwood machine problems where we'd have to look at how each separate part of the system before we um, before we look at the overall acceleration of the system. And in this case, it was different because the pulley has angular acceleration, so we had to make that connection between translational acceleration and angular acceleration. Um, I'm hoping that this whole problem is going to be a little easier if we do it in terms of energy. What do y'all think? Do you think doing it in terms of energy is going to be easier? Yeah, you could use energy. So we're going to do the same problem except terms of energy. Okay. Okay, here we go. Now we're going to go to the same question, except we're going to do it in terms of energy. So still calculating acceleration, just now in terms of energy. So remember our initial scenario. Um, we have the weight up here, and the weight's going to drop. So how do we, some main points that we have to kind of talk about in this scenario. When when we looked in terms of energy, we had to look at energy of the system. So we have two parts of our system. We have the wheel and we have the block. So we need to look at these energies like together. Even though it's two different parts, we're looking at the whole system. So the system includes the block, the wheel, and the planet. Earth. So if we wanted to do an LOL diagram, we could, go back to that kind of idea. Um, so let me just draw it up here. L, that's a terrible L. O, L. So we said in here is in the system is the wheel, the block, and planet Earth. And let's see what kind of energy initial we have. So I think we set it up as like ME, right? Initial equals ME. Oops, I should have put some. Do, 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 do. So we have to imagine that the block is up here, right? So what kind of energies do we have initially? Yes, thank you, Mia. Thank you for saying that we're using the law of conservation of energy, and that's how we approach energy problems. Is we always look at it with that initial law of conservation of energy. So imagine the block is up here, right? This is the block. Okay, this is our first spot. What kind of energy does the block have? Or the wheel have? Yeah, there's UG. Oh, by the way, the wheel is not moving initially. So are there any other energy initials? Do we have any spring potential energy? Do we have any kinetic energy? Do we have any kinetic energy in the wheel? Yeah, we don't have spring potential, and we don't have any kinetic energy initially because I said that the wheel is still and so is the block. So the only energy that we have initially in the system is the gravitational potential energy in the block. Okay, so what's our final potential energy then? So the block drops, right? And it goes down to, we'll call this our 0 mark. So what's mechanical energy final? And I hope you can imagine this scenario of a wheel and a block attached to it, and what would happen if you release the block. Be specific, what type of K? Because we have kinetic energy rotational and we have kinetic energy translational. The question is, what is our mechanical energy final? So we have all that gravitational potential energy, and where is it going to be converted to? Yep, we're going to have Kr, or Ker, kinetic energy rotational, because the pulley is going to rotate, right? And then plus, we're going to have translational kinetic energy because the block is going to be falling. Are we okay? Again, the two problems that we're doing today are rather difficult problems. That's why we're spending so much time on them, because there's a lot to go over for these problems. A lot of old stuff coming back up. Okay, any other energies? In our mechanical energy final? Okay, I'm going to assume no, and that you guys are starting to derive. So go ahead and derive this out. UG is also known as what? Equals derive rotational plus derive translational kinetic energy. And y'all need to give me that derived expression. Okay, so what is that expression derived to? You can send a picture in, or if you just want to unmute yourself, you can verbally tell me too. Okay, thank you, Mia. That's the first one. I have headphones on, so it won't be in the video if you tell us the answer. Thank you. Kinetic energy rotational is 1/2. Moment of inertia, omega squared. Plus 1/2, thank you, Jayla, mv squared. That looks cute. Okay, where do we go from here? This looks awful. No, Gabriel, we don't have to do that because I is given to us here. Because we don't have the mass of the wheel. Let me remind you of something, because this is going to come up in the problem later. When we're looking at mechanical energies initially and finally, we're looking at their max, okay? So when we look at this kinetic energy translational, we're looking at the velocity final here, okay? So this is VF that we're looking at. Let me try and clean that up, okay? And remember, what we're trying to get to here is the hardest problem or the hardest variable to solve for, and that's why we're doing it. We're trying to get here, linear acceleration, right? So you should intuitively know that if the block starts at rest, velocity initial, and if we solve for velocity final, then we should be able to get acceleration pretty easily, right? Because linear acceleration is velocity final minus velocity initial all over time, and we can kind of figure out how we're going to get to solving A. So basically, what I am trying to give you a clue to do is to get an expression that solves for velocity final. So we have a velocity final here. What can we do elsewhere to get a velocity final? Yes, excellent job, Gabe. So we have MGH. Ooh, that looks terrible. So that would be the next step, is to take care of that angular velocity, because there's nothing we can do with it. We don't want it. We can change that into linear velocity. Okay, so remember, velocity linear is omega times r. So if I want to solve for omega, that's velocity over r equals omega, and then it's squared here. So it's, hold on, let me fix that. Velocity over radius, parentheses, squared, plus, and this is velocity, or final velocity. Yeah, Mia, we're, the next step is to actually put some numbers in there. And, but there's one thing that there's two variables whose numbers we don't have right now. So we're going to have to leave them alone. Yeah, we're not deriving I because it was given to us. So we don't have a value for H, and we don't have a value for velocity final. The rest of it we have values for, okay? So let's go ahead and do some number crunching. to see what numbers we can get, and leave H alone, leave velocity final alone, because there's no number substitution we can do. So substitute mass, gravity, I, R, and M, and give me some numbers that can go in front of those variables that we don't have. So for example, mg, h, and we have little m, we have g. So 4 times 10 is 40h. It doesn't look good. Equals, and then what number is going to go in front of VF squared here? And then plus what number is going to go in front of VF squared here? Yeah, good, Gabriel. So this one's 4, and this one's 2. Okay, so simplifying that further, we have 40h. Leave h alone because something magical is going to happen later. 6bf squared, right? And that's gonna, we're gonna solve for VF. Keep H in there because I'm telling you something magical is gonna happen with it. So I know it's bothering you right now, but kind of leave it in there. What would VF be equal to? Good job, Gabriel. Awesome. I'm just gonna put it as a number. So square root of 6.67h instead of leaving the 40/6. Okay, y'all, we didn't even solve for acceleration. We only solved for a velocity final. So what we did before, and we did it rather quickly when we were learning energy, is sometimes we would take velocity final from our energy equations, and we would use the kinematic equations to take the final velocity and solve for other things. Okay, so for example, we would take like final velocity and we would solve for the distance that an object traveled. So we can actually go to one of our kinematic equations and we have the variables that we can solve for. So let's pick a kinematic equation that we can use. And it might be hard to figure out because we have that h left over. So we want to solve for linear acceleration. We have velocity final. We have velocity initial that's at rest. Yes, velocity is in the y direction. So you could say final velocity and y if you really wanted to. Yes, Gabriel. Do you see what's going to happen? I get like so excited. I thought this was a really cool problem to do. Yeah, so normally we say this is delta y here, but we can also recognize that y is h. Okay, so we can do some number plugging. So square root of 6.67h, but this whole thing is squared here. Velocity initial is 0, so I'm not even going to write it. 2 a h. And remember, we want to solve for a here. Right? There it is. We're almost there. And what's really cool, Gabriel, did you figure out what's going to happen yet? Yeah, the square root cancels out, so I'm just going to erase that. Okay, but that's not the exciting part. Oops. Everybody brought height to the party. Such nerds. Okay, I am. Yeah, so the height doesn't matter. Isn't that crazy? And look, we're there. And guess what the answer is? Jayla, you went away. Or maybe she just already has my answer. Oh, okay, Jayla. Yep, same number. Okay, so, wow. These were two very difficult problems. I'm not saying that these are something that you should be able to do, but the reason I wanted to do these is because solving for linear acceleration was going to be the most difficult variable to solve for. So just keep in mind of what this process looked like and some of the things that we had to do, some of the concepts that we had to go over in order to get to linear acceleration of the system or of the small block. and, be ready to solve for other variables, because this scenario that we solve for, I could ask you for any variable. I could ask you to solve for moment of inertia. I could ask you to solve for the mass of the wheel. And you would have to be able to figure out how to make those derivations in order to get to um, a valid answer. So that's all I had planned for y'all today. I know that was a lot. That was a lot of good work. We went over dynamics in the first part of the question. We went over energy. So we did a lot of good review and a good addition to rotational motion. So keep working. You guys are doing an excellent job. I'm really proud of you. Um, I'm hesitant to put up another week of Schoology because I'm just not seeing a lot of students finish the 3 assignments that I've already had on there. But when I look through my list, I do have students that are done with all 3 things, and I hate having to have those students wait um, for the next um, for the next topic. So my idea was to get Schoology up so that I can move a few on. And tomorrow I was going to start moving on to some, um, either it's going to be new material or I'm going to do a problem similar to these two, except with 2 hanging masses. I'll decide. I'll see what I want to do in the morning, um, and we'll figure it out from there. Okay, I'll be on till 3 p.m. Let me know if you want to do another go live and solve some more of those rotational um, motion uh, problems, the 10 problems that I assigned to you before spring break. Just let me know, okay? I'll be on till 3. Thanks, guys. Have a good day. Miss you.